Good morning, foreign wanderer. Hope you had a wonderful Thanksgiving. Hey, thank you. I did have a wonderful Thanksgiving. How was your Thanksgiving? Good morning, Chen. Good morning, Hash Brown Swag. What was on the dinner table? Let me tell you what was on the dinner table. Well, I mean, let's get turkey out of the way. The obvious. There was a big turkey. Good morning, BJ Reiner. And I feel like we had 4 different types of potatoes on the table. Like there was a sweet potato. There was like your standard mashed potato. And then there was this other like potato thing that looked like it had some like nuts in it, and it was kind of sweet. I think that was potato, maybe it was squash. So I arranged little pockets of each type of potato around the circumference of my plate. And then I had turkey right there. And then I put cranberry on top of that turkey. And then I had some like peas over here. And let me tell you what I'm impressed with. Good morning, Belkut. The tendency for many people is to just load up their plate, right? And then they don't finish it. I cleaned that plate. There was not a thing left. But let's not forget about the rolls. The cute little rolls that you load up with butter. I had some of that, and I had a slice of chocolate pie. It was kind of like a pudding pie. Hey, good morning, MCAT. What'd you guys have? Is it anywhere near the spread that I just described? If you're Hispanic, you need to finish that plate. Hey, there you go. That's good tradition. You better finish that plate. Had a lot of pie. What kind of pie? Different types? Apple pie? Renee, my mother says, what did you cook? Because you are quite the chef. I actually didn't cook. I didn't cook. The family, the uncles, they had it under control. I just ate it. MCAT, cherry and pumpkin pie. Foreign Wanderer had pig shoulder. Pernil. What? What are we talking about here? What are we talking about? Boneless pork shoulder, orange adobo seasoning. Oh, this sounds good. Chin had hot pot. Ooh, I love hot pot. What did you throw in the hot pot? Puerto Rican pork shoulder. Plan on cooking for me when you come to Arizona. You got it, Mom. Whatever you want, we will make it. Maybe some salmon. I'm an expert at cooking salmon. You put everything in the hot pot, says Chin. Yeah, that's what you should do with hot pot. A little bit of everything. But hot pot, it's very thinly sliced meats, right? Or at least that's what I enjoy most in the hot pot. Very thinly sliced, like beef, Boom, throw it in there. Hotman5683 says, hello. Hello. Good day to you. Oh, wow. Okay, well. I hope you didn't eat too much. Abhinav, good to see you. Professor Estes, how was your Thanksgiving? Oh, it was good. Another interesting thing that we did, aside from the food, are you guys familiar with the corny Christmas movies produced by Hallmark or other similar entities? Now, if you've seen any of these, you know that they share a lot of things in common. Like this unlikely couple getting together and then they kiss in the snow. But then there's drama with an ex-boyfriend or girlfriend. Okay, so what we did, because we know that these types of things will be happening, we made a bingo game. Alright? Where you make a grid, and in each square you put one of the stereotypical things you expect to happen in the movie. And then as you watch, as each thing happens, you cross it out. Trust me, you'll get a bingo. Trust me. Okay, we're going to do an example today. It'll be some nice review. It'll get us back on the same page. So, let's get right into it. So we've been discussing load transfer. When you corner, the weight shifts to the outside. All right, so we're going to look at a Corvette Z06. And here I have some vehicle specifications. We'll be coming back to these. We'll need to use these because we're going to have some questions related to cornering with this vehicle. So we'll come back to this. But let's look at the static tire loads. And let's just start breaking down some basic characteristics of the vehicle. Because you'll notice up in the table up here, there's a couple things I left blank. Like the weight, the front weight distribution. Actually, these will be pretty easy to calculate. This one will take a little bit more work. The height of the CG above the roll axis. So first we'll knock out these quantities and fill out these vehicle specifications that we're going to need later on. Okay, so these are the static tire loads on each tire. So these are the normal loads, the vertical load on the tire. And you'll see that the right front, right rear, left rear, they're all the same. So let's first get the mass from here. So the vehicle mass, number one, can be determined from the tire loads. So the mass is going to be the weight of the car, which let's get the weight first. That's the load on each tire, and we got to multiply it by 4. So that'll be the total weight of the car. And then we need to divide this by gravitational acceleration to get the mass. All right. And if you punch these into your TI-83, or maybe you have one of those solar powered calculators. Do you guys know what I'm talking about? The old school ones. You're going to get 1,600 kilograms. So that's the mass. We determine that from the tire loads. What about the front weight distribution? Well, I already wrote it here. It's clear that every tire is equally loaded. So 50% of the vehicle weight is on the rear and 50% of the weight is on the front. So we call this a 50% front weight car. Sportier cars, it's going to be close to 50%. Sometimes the weight can even be a little bit towards the rear, especially if you have an engine in the rear, which is pretty rare. Okay, so the front weight distribution is 50%. So the distance from the rear axle to the CG, that's going to be our front weight ratio, which is just 0.5 times L, which is the wheelbase. Shouldn't it be 3932 times 4, not 3924 times 4? Oh, good grief. Wait, why did I write 24? Thank you very much, Johnston. Wait, is my number still right? I don't know why I wrote 24. Okay. So the distance from the rear axle to the CG is the front weight times the length of the wheelbase, which is 2.73 meters. So we got 0.5 times 2.7, or wait, was it 2.71 meters? I got to check the table. 2.71. Okay. So that's 1.355 meters from the rear axle to the CG. And if you want the distance from the front axle to the CG, you just take the total wheelbase, you subtract that distance just above, because these two distances have to add up to the wheelbase, and they're equal. So not unexpected. 50% weight distribution, so these distances should be the same. Okay, so we have the mass, we have the weight distribution, we have LF, LR. Now, what I want to do is get some geometry related to the roll axis here, because this is going to be important for load transfer. So we're going to draw on this figure in a second, but we want to get the height of the roll axis. Well, let's just start filling in things. We're going to need the height of the CG above the roll axis, but first we need to define the roll axis here. So the way to start is first to define the height of the front roll center. So that's going to be the height of the roll center at the front axle, the height above the pavement. And you can figure out where this roll center is by looking at the front view of the suspension linkages and determining the instantaneous center, which we did a little example, maybe it was a week or two ago. Maybe we'll do another one of those later. Okay, but for a sporty car, the roll center at the front, it's going to be pretty low to the ground. From our table, the height of the roll center at the front axle is 0.076 meters, which I think is just like a couple inches. And at the rear, it's a little bit higher, but still very low to the ground. Something like this. So the height of the roll center at the rear is 0.191 meters. Now the roll axis is when you connect these 2 points from the front to the rear. Let's get like a green color here. So I'm going to take the front roll center. I'm going to extend it back to the rear roll center. Connect them. And here we have the roll axis. Now this is the axis about which the chassis rolls when you're cornering. And this roll axis, it'll actually change a little bit as the body rolls, but we're assuming that it's going to remain constant. A pretty good approximation, but not perfect. Okay. So we're gonna locate the CG here, and that depends on the weight distribution. So, okay, first let's define this dimension. The wheelbase, L, 2.71 meters. Now, where is the CG within the wheelbase? Well, you can use LR or LF. And so this is a 50% front weight distribution, so it's right in the middle of the wheelbase. Let's try to draw directly in the middle. I'm judging this by eye. Looks perfect. Looks fantastic. So this distance that I'm marking out is LR, the distance from the rear axle to the CG. And we calculated that to be 1.355 meters. So just half of 2.71. Now the CG, we have the CG height. Wait, let's draw like a little line right here, because the CG is going to be located along this line. And it's a height of 0.46 meters. What is that in the table? 1.5 feet. All right, so we're going to try to draw the CG 1.5 feet above the ground. So I'm going to draw a circle. And I'm going to say this is 1.5 feet. And then we're going to use artistic skills to really dial this in. Come on now. Nice, says CP Alpha. Thank you. I expect all of you to spend as much time and care as I just did when you're drawing your CG. Okay, so we know that this CG is 0.46 meters above the pavement. One and a half feet. All right, now when we're doing load transfer, we're interested in the height of the CG above the roll axis. All right, so I'm talking about this height. Height of the CG above the roll axis. So that's a subscript R on there. So we're going to have to use some trigonometry to figure this out. I have a way that I like to do it, and I'm going to show you below. Okay, so the height of the roll... First, let's just make a function for the roll axis. So the height of the roll axis above the pavement can be calculated along the wheelbase using the geometry that we provided up above. All right. So let's just call the height of the roll axis okay. So, okay, let's say, for example, at a distance LF from the front axle, which is just where the CG is located, this is going to be the height of the roll axis. So I'm going to think of this just like drawing a line. Like at the front axle, the height of the roll axis is the height of the roll center at the front. And then, how does the roll axis change? Well, it has some slope as it goes towards the rear axle. So you can see that this is slightly inclined upwards because the roll axis or the roll center is higher at the rear. So what is that slope? Well, it's going to be the height of the roll axis at the rear minus the height of the roll axis at the front divided by the wheelbase, right? That makes sense. That's the slope. And this slope relative to the front axle, it's increasing over a distance LF. So this is going to be the height of the roll axis at the CG. So to get the height of the CG above the roll axis, we just need to take the height of the CG above the pavement, subtract the height of the roll axis at that point. And why don't we just substitute what that is? So it's the height of the roll center at the front plus this slope acting over a distance LF. So let's plug in some numbers. Let's get the height of the CG above the roll axis. So it's 0.46 meters minus 0.076 meters, 0.191 meters minus 0.076 meters over the wheelbase, 2.71 meters. And then LF, what is that, 1.355 meters? Okay, and then we get 0.3265 meters. So like a third of a meter. Let me ban that thing. Okay. Whew. Okay. So I think we have everything we need. Now let's introduce the cornering problem. We have all these dimensions and stuff. So here's the story. While cornering to the left on a skid pad of radius 150 feet, the Corvette reaches a maximum speed of 51.9 miles per hour before the tires start to lose traction. So this is just like a standard skid pad test to determine the maximum lateral acceleration capabilities of the Corvette. Now, sensor data indicates that the roll angle at this maximum acceleration was 3 degrees. Positive 3 degrees of rotation about the longitudinal body axis. So based on this information, let's estimate the total roll rate, K phi F plus K phi R. So that's like the resistance to rolling, like a torsion spring, for the Corvette. Okay, so let's do it. The first thing we need to do is we have a formula for what the roll angle of the sprung mass is. The sprung mass is the mass above the suspension. We derived this using Newton's laws. So we have the mass times the lateral acceleration times the height of the CG above the roll center, which we now have, divided by the total roll rate, K phi F plus K phi R. Okay, so we have mass, we have the height, the angles given to us. We're solving for this total roll rate. We need the lateral acceleration because we have not calculated that yet. So the lateral acceleration we can determine from the kinematics of circular motion. The car's moving in a circle on the skid pad, and so the lateral acceleration, at least the magnitude of it, is the velocity squared divided by the radius of the circle. So we were moving 23.2 meters per second around this 150-foot radius skid pad. So we square that. We divide by 150 feet, but in SI units. And we're going to get 11.8 meters per second squared of lateral acceleration. So what is that, like 1.1 Gs or something? Now, this is the magnitude of the lateral acceleration. But let's remember the vehicle's making a left turn. So in SAE coordinates, Society of Automotive Engineers, if you're Accelerating to the driver's left, that's a negative sign. So AY must be negative. If we were cornering to the right, it would be positive. Okay, so now we can solve for the total roll rate because we have everything we need to plug into this equation right here. So here we go. This is 3 degrees. So we're just using the formula up above. So we have the negative of the mass, which we got from the static wheel loads. We have minus 11.8 meters per second squared, which we got from circular motion kinematics. We have the height of the CG above the roll center, which we got using trigonometry. And so this is divided by K phi F plus K phi R. All right. So then if you just, move this over, solve for it, you're going to get 118,950 Newton meters per radian. That's the total roll rate of the vehicle. So a pretty stiff suspension overall, which results in only 3 degrees of body roll at over 1 G of lateral acceleration. So if you did this in, a minivan or something, you would expect, 6 or 7 degrees, 8 degrees of body roll. If you could even get up to a G of lateral acceleration, I don't think you could in a minivan. Okay. Now, here we go. Let's make this a little more realistic. So this is our total roll rate here. But let's assume that 60% of that roll stiffness is allocated to the front track, so your front suspension. So that means that K phi F over the total roll rate is 0.6. So what we're going to do, assuming that 60% of the roll rate is at the front, we're going to get the normal loads on each of the 4 tires during that skid pad test. We're going to predict them. And we'll come back here and, fill in these boxes with those loads. All right. So let's first write an expression for all of the tire loads. So left front, left rear, right rear. So these are the formulas we've been using. I don't think I'm having buffer issues. Is the stream okay for everybody? Okay, cool. No buffer. All right, so these are a little bit of lag. Okay. Not too bad though. So each of these you start with the static load. Stream's fine for Jenna. Perfect. So I'm just going to put the static loads here. These are the loads on the tires when it's just sitting still on the pavement, not cornering or anything. FZ at the rear. So this O that I'm putting down there, that just indicates the static load. And because this was 50% front weight, the static loads are the same for every tire. Okay, but when we corner, we're going to have load transfer. So we're going to have this delta in the normal load minus. And so we're going to use a formula for this delta. The sign of this term can change depending on the direction of cornering, which is perfect. Okay. So let's fill in what we know so far. We have the static loads. And then we'll just have to add in the load transfer. We'll put that in. All right. So what is the load transfer at the front? We have this expression. The mass times the lateral acceleration divided by the front track width times LR over L, which is the front weight distribution, times the height of the roll center at the front, plus the front roll stiffness distribution, so that's K phi F over K phi F plus K phi R. So this will be 60% right here, times the height of the CG above the roll center. All right, let's crunch the numbers. We have the mass, 1,603 kilograms. The lateral acceleration, the sign is important here. Minus 11.8 meters per second squared. We're cornering to the left. We have the front track width, 1.6 meters. This is going to be a little different than the rear track width. I think the rear track is a little bit wider. Okay, the front weight distribution, 50%, 0.5. The height of the roll center at the front, 0.076 meters. And then we have 60% front roll stiffness, so I put a 0.6 there. And then we multiply by the height of the CG above the roll center, close to 1/3 of a meter. Okay, 2,768.7 newtons. So it's a positive number. Let's look at the rear. It's a very similar formula. Mass times lateral acceleration, but now we have the rear track width. So when you compare these two formulas, think about what you can do to modify front versus rear load transfer. LF over L, height of the roll center at the rear. So like, for example, if you compare the roll center heights, for the Corvette, the rear roll center is higher than the front. Well, why would they make a decision like that? Well, if this is higher, it's going to increase the load distribution at the rear. And remember, the whole point of dialing in the load transfer at the front and the rear, making them different, is it comes down to how much grip you get at the front and the rear tires. And you want to be modifying that relative grip so that the vehicle is probably neutral steer. Because neutral steer has some nice properties, like the front and rear slip angles tend to be the same, which means you're getting like maximum juice out of all of your tires. Okay, let's keep going. The rear roll stiffness distribution. Height of the CG above the roll center. Okay, so a lot of this will be exactly the same. The rear track width. Oh, actually, it's a 1/20 of a meter shorter. So the rear tires are slightly closer together than the front tires. So reducing the track width at the rear also increases load transfer at the rear, because the wider apart your tires are, the less load transfer there is. If you bring the tires closer together, there's more load transfer. Okay. So, okay, we got the rear weight distribution, which is also 0.5. The CG's right in the middle. The rear roll center is 1.19 meters above the ground. Okay, if 60% of the roll stiffness is at the front, that only leaves 40% at the rear. And then we got 0.327 meters. Now, where do you think more load transfer is happening? At the front or the rear? The rear has a higher roll center, but it has less roll stiffness. The stiffer the suspension is, more load transfer happens at that axle. So it's interesting. The load transfer comes out very similar at the front and the rear. Just a difference of a couple newtons. That's what I find really interesting about this. So like at the rear, the roll center and the track width make it relatively have more load transfer than the front, but because the front has a stiffer suspension, that also gives more load transfer at the front. So it's kind of like the load transfer's equaling out by different mechanisms. At the front, it's because of the suspension stiffness, and at the rear, it's just more geometrical. Okay, so given these numbers, we're going to go calculate the tire loads. So we got to go back up here. So let's talk about the front. We're going to add plus delta FZF, which was plus 2,768.7 newtons. So we're going to get minus 1163 newtons. Now, every time you do these calculations, do a double check here, because what's happening physically to the front left tire, well, it's actually losing normal load. The front left tire is lifting off a little bit, and now there's a little bit of weight. I mean, there's less weight on it. Does that make sense in a left-hand turn? Okay, and then this right one. It's gaining load. 601 newtons. Do these numbers make sense to your intuition? Left tire loses load, right tire gains load. And we're cornering that way. Pavlo says, yes, it makes sense. Foreign Wanderer, could you explain that again? Yes, yes, yes. Okay, so imagine yourself. Imagine yourself smiling, driving this cool Corvette. Here's the steering wheel. And you're turning to the left. What are you going to feel And actually, what is your friend going to feel over here? When you turn that steering wheel to the left, it's like you feel yourself being like pulled this way. We've all experienced that. And the car is actually like rolling that way towards the left-hand side. So we are putting more weight on the outside tires. Yes. Good, good, good. So this is a double check I always do in my mind. The outside tires are gaining load. Good, good, good. All right, let's do the rear. So 2761.6 newtons. So now we gotta do this. So they have similar load transfer, but for different reasons. That's part of the fun of cars, that there's more than one way to get to the same place. That's why we have very different looking cars. Racing is a very dynamic sport. Things are changing. All right, and so we see we're cornering this 150-foot radius skid pad. We're turning left, and we have much more load on our outside tires than our inside tires. And it's at this point, and there's 3 degrees of body roll that direction. It's at this point that the tires start to lose traction in this test at a little bit over 1G. All right. One more question. One more question here. This is interesting. Assuming that the car remains unmodified, whatever, same car, what would be the theoretical minimum magnitude of the lateral acceleration that would be required to lift a tire off the ground? And what does that mean, to lift the tire off the ground? Well, by definition, we'll just say that that tire now has no normal load acting on it. Enough load has transferred that the pavement doesn't have to produce any reaction force because the tire's just like floating. And which tire do we expect to lift off first? Okay, so let's talk this through. And this situation is actually pretty unrealistic, and I'll get to that. So we found out that slightly more load transfer happens at the front for this car. And the static normal loads are equal front and rear. Well, and we just mean the weight front percentage is 50%. So they all start at the same place. All right. For that reason, we expect a front tire to lift off first. Because they start with the same static load. But more load transfer is happening at the front. Okay, so when is this going to happen? Initiates. So liftoff is going to initiate when delta FZ at the front, so the amount of load transfer, is equal to the static load. Okay, Chin has a question. So can we consider the height of CG and the roll stiffness distribution as two cost functions when design our roll part on the vehicle? It should generate a 3D curved surface about FZ. Okay, so Chin is talking about, what if I'm trying to optimize my load transfer? And I think you're saying you could have two separate cost functions, like load transfer from geometry and load transfer from suspension. You kind of treat them separately. Can we do that? Because you have these two terms added together. Well, hold on though. I don't think they're totally independent. Because this term affects this term. Because that'll change the roll axis. That's tricky. And, yeah. It's tricky. Okay, so we're gonna have liftoff at the front when the amount of load transfer is equal to the static load. So oh, try it. Yeah, Chin, let me know what you find. Okay, so we're gonna get 3932 newtons. That's the static load. So what I'm going to do, because we want to solve for the lateral acceleration where this happens, we're going to go back up to this equation, but we're going to assume that we already know what the load transfer is, but we're going to solve for the lateral acceleration as the unknown. So we just have to manipulate this equation to get the lateral acceleration by itself. Okay, so I got that. Okay, I guess I was gonna put that there. Okay, so AY negative delta FZF times the front track width divided by mass times the front weight distribution, the height of the roll center at the front roll stiffness distribution, height of the CG above the roll axis. So that's just isolating the lateral acceleration from that. And if you plug in all of the numbers, this is still for a left turn here. Minus 16.8 meters per second squared. How many G's is that? 16.8 divided by 9.81. 1.7 G's, which actually is not uncommon for formula cars. Not at all. Like a formula car, it can get like 4 G's, something like 6 G's in a corner. But that amount of lateral acceleration, boom, it would flip over a Corvette. That's kind of funny to think about, isn't it? But I have a point to make here. But this would likely never happen in a Corvette. Because the tires are responsible for producing this lateral acceleration, right? So where does the force come from? It comes from the tires. Are responsible for producing this. Let's just say producing the lateral force. But the tires start to slide before this maximum, or before this force is reached. So, let's go back to this figure to explain this a little bit. So how does a tire produce force? I mean, lateral force. So we have Fy. Well, it produces lateral force with slip angle. And the function looks something like this. Right? And there's a... And this function changes with normal load too. Like if I put more weight on the tire, it's going to look something like this. So it kind of gets steeper the more normal load you add. Actually, this peak should be shifted over a little bit. But anyways, you can tell that at a given normal load, there's a maximum amount of lateral force that you can achieve. And if the tire slip angle goes past this threshold, then the amount of lateral force drops off and the tire starts sliding. And I don't know if they like specifically design sports cars this way, but the tires will start to slide before you reach the point of producing enough lateral force to actually flip the vehicle over. If the car is designed nicely. Now, of course, a good test for this, I mean, I've showed you this before, but it's good to pull up again. The Moose test. So you, let's watch that again. It looked like the front, it's that front tire that picked up. Let's see what else is going on here. Front tire picked off.
Fifth generation of Toyota RAV4 sing effect through the car's movement. There's a bouncing effect.
Little dangerous.
The test that we tested two
front
different Toyota RAV4s with the same result. Poorly the RAV4 performs. Will show you.
Now, what I think is that you can prevent. So this kind of rollover situation, this is caused by lateral acceleration. Like what's happening here? They have some speed, and then they're doing a sharp lane change. So it's like a tight radius. It introduces a lot of lateral acceleration, and then that load transfer is picking off one of the tires. but I think it's more favorable or more safe to design your car so that the tires give out before it can produce enough lateral acceleration to flip the car over, you know. If you have a car with the CG that's lower to the ground, like a Corvette, you can afford to allow that car to produce more lateral acceleration because it's not in danger of flipping over as much because it has geometrical properties that prevent it from transferring all that load off of the tire. What's going on here? Let's see another one.
An all-time best ever level for any test car through the Moose test. Maximum speed is 84 kilometers an hour. A marvelous result.
So this car does very well.
Best ever level for any test car through the Moose test. Maximum speed is 84 kilometers an hour. A marvelous result. It's 2,620 kilos fully loaded, or about 400 kilos more than the Toyota RAV4.
Oh, that does okay.
The Kia Sorento managed speed system makes wonder. 84.
Wait, I wonder if they have a Tesla doing a Moose test. Do they do that? Oh. I've never watched this. Okay, you guys know Tesla, right? Has the battery super low to the ground. I'm curious. Wait.
Tesla Model 3. Maniobra de esquiva. El Tesla Model 3, con el que estamos realizando una prueba de larga duración, ha dado un resultado muy bueno en la maniobra de esquiva y slalom. En este vídeo os enseñamos cómo reaccionó en ambas pruebas. Las condiciones en las que las hicimos, así como la degradación sufrida por los neumáticos, las detallaremos en un artículo del blog específico que hemos creado para esta prueba de larga duración, y cuyo enlace podéis encontrar en el apartado de descripción. Asimismo, hemos hecho un vídeo adicional. Reaccionar el coche ante esta maniobra la hicimos a 74 km por hora y no a 77 como es el objetivo, por un error nuestro, dado que no siempre es fácil atinar con precisión. En cualquier caso, tiramos un cono, pero las reacciones fueron seguras y fáciles de manejar. Las luces de freno permanecen encendidas durante casi todo el ejercicio y esto lo veremos a lo largo de las diferentes pasadas que mostramos en este vídeo. No es porque pisemos el freno,
you guys know, it's distributed all along the wheelbase, low to the ground.
Bien por la frenada regenerativa.
Tesla is surprisingly good on track if you use good tires and brakes.
Hay dos niveles, bajo y estándar, siendo estándar el que más frena el coche al soltar el acelerador.
I imagine it has just like really great load transfer properties.
Al pie del acelerador.
But it comes at the cost also of it being so heavy. It's super heavy.
En ningún momento.
Way heavier than any other sports car.
Muy a gusto con la respuesta del coche en su conjunto. Las ayudas electrónicas a la estabilidad intervinieron de forma moderada y sutil, actuando con la exactitud necesaria para que el conductor prácticamente no se percate. El coche pierde menos velocidad al levantar a la que intentamos ejecutar la maniobra de esquiva. No la conseguimos realizar de forma satisfactoria, pero se puede. Además, la dirección es rápida, tiene buen tacto y una gran capacidad para guiar al coche con precisión. Estamos muy satisfechos con el rendimiento del Tesla
you
Model
see,
3
like once they get these higher speeds, it starts to just slide. So the tires are losing grip, and so it's not producing enough lateral acceleration to flip itself over.
En el blog específico que hemos creado para la prueba de larga duración del Tesla Model 3, cuyo enlace
it looks like
en la
the rear starts to slide out.
Damos más datos de le cuesta poco cambiar de dirección. Esto junto con una buena adherencia con el rendimiento del Tesla Model 3 en la maniobra de esquiva y con el de los neumáticos.
Yeah, it looks like the rear outside tire starts to lose traction and it kind of oversteers a little bit.
No han sufrido un desgaste excesivo cuando los hemos sometido a esta prueba tan...
Very interesting. Very interesting. So whenever you watch these videos, you can think about the load transfer and what's going on there. Very fascinating. Okay, guys, that is wow, it's 11:20. that's our example. I wanted to do this because we've derived a lot of formulas, and I think this example uses most all of the load transfer formulas that we've looked at, and so it kind of makes it more concrete what we're doing here. So, let's see. We have, okay, bye-bye virtual assistant. Virtual assistant, by the way, is a chat bot. It's like an artificial intelligence. And it fooled me before because I thought, like, it has pretty sophisticated chat, and I've talked to it like a real person. And then I felt foolish. They also have a vid of the Model X doing a moose test. Oh, let's look at that.
Tan exigente. En el blog específico que hemos creado para la prueba de larga.
Oh. Okay, we'll look at this one.
Es precisamente un modelo ágil. No hemos conseguido realizar la maniobra de esquiva a más de 70 km por hora, que es una velocidad baja.
Doesn't it feel like they're kind of close to that barrier over there?
No hemos sido capaces de
Couldn't they like scoot it back a little bit? Like it feels like you're gonna run into that thing.
En el primer giro para evitarlo, no hemos podido hacerlo sin derribar bien el último cono interior del primer pasillo o bien el primero del segundo.
Wow.
Los más de 2,000
Well, I'd like to see a GG diagram from this too. I wonder how many G's. Hey, see you later, Jenna. Oh, we got a bird.
No nos hemos encontrado ha sido
oh, narrowly evading death.
Slalom. En el slalom hemos experimentado las mismas reacciones que en nuestras pruebas en carretera. El Model X gira casi plano, moviéndose muy poco la carrocería y si se intenta dar un pequeño golpe de gas para colocarlo entre cono y cono, se consigue la reacción contraria, un leve subviraje que lo aleja de la
It seems like it's fantastic in cornering. Wait, what? How many cars do they test? What?
Entre otros factores, a unos
Look at this thing.
Al aumentar ligeramente la velocidad hasta 81
Are you kidding me?
por hora, el eje delantero comienza a subvirar, pero las reacciones son prácticamente
las
mismas que en la anterior pasada. Tras revisar el vídeo, una vez hecha la grabación, nos dimos cuenta de que el cono derribado con la rueda trasera derecha no estaba bien colocado.
Okay, wait, I want to see.
Prioridad, ya que no las que no intervenía.
Oh,
en la primera de ellas, la de color blanco. Del Sanyong XLV probamos 2 unidades. En la primera de ellas, la de color blanco, el control de estabilidad tenía un funcionamiento irregular.
Kind of a difference
porque había
there.
ocasiones en las que no intervenía y se producía una pérdida total del control del vehículo. En ningún caso fue posible saberlo con anterioridad, ya que no había un testigo o alarma que indicara.
It looked like our inner tires. Yeah, well, that one, the rear inner tire lifted off. It looked like.
Sanyong nos cedió una segunda unidad de XLV para determinar si el problema era un caso aislado o algo generalizado.
Rear inner tire.
En esta segunda unidad, el control de estabilidad funcionó en todas las ocasiones.
Lift
No
off.
obstante, siempre echamos en falta una intervención más contundente de este sistema, que frenara más el vehículo para facilitar la realización de la maniobra de esquiva. Siempre la trasera e interior al giro.
Oh, buddy.
La velocidad máxima a la que hemos superado esta prueba sin tirar ningún cono ha sido 72 km por hora.
Gosh, I could probably just watch those all day. All right. That's it for today. We'll be back here on Wednesday. I need to put up a short homework assignment because we have one more homework assignment, one more group project. So I'm going to try my best to get up a short homework assignment today that we can do this week. Next week, we have our final group project, then we're done. Hey, MCAT, see you. Have a great, see you Wednesday. Have a great Monday. Everybody, have a fantastic day. It's good to reconnect with you guys. It feels good. It's a pleasure to hang out and study vehicles with you. Hey, have a good one, Foreign Wanderer. Belcut. See you.